So, today I will try to finish the remaining article of unit 1, that is continuity equations. Okay. So, these continuity equations are very important because they origin from the fact that the charges can neither be created nor be destroyed. ना तो चार्ज को क्रिएट किया जा सकता है, ना उन्हें डिस्ट्रॉय किया जा सकता है. Okay? So, this is the basic premise behind this continuity equation, but it plays a significant role in electromagnetism. So, I will write that it is origin from the fact that charge can neither be created nor destroyed. So, this is the basic premise behind the continuity equation. So, when we talk about charge, definitely continuity equation is going to talk about electric field, and now we have started to understand that every electrical parameter, whether it is potential difference or it is electric field, magnetic field or current, all of them are interrelated, and the differential equation governing the relationship between them. There are certain, I say that magnetic field and electric field are related, but I know that there are certain differential type of equations which are governing the relationship, the way they will behave together, and we call them as Maxwell's equations. Okay? So, these equations tell us that how all these quantities are related. So, if suppose I have a small cylindrical surface, you can consider it as a wire or a pipe, okay, and it is perfectly conducting. This surface, this small surface, the cylinder is perfectly conducting. So, it means it is perfectly conducting. And this conductor allows only one type of charge. There can be n number of charges, right? An ionized molecule is, an ionized atom is also a charge. Okay? So, it has a charge of type Q. It has charge of type Q, and I assume that there are n number of such charges present per unit volume. There are n number of, n is the, Q is the charge, and n is the number of charge carriers present per unit volume. Now, I assume that all these charges, there are n charges. Okay. So, they are, if this is, and this cross sectional area is dA. Okay. dA is the cross sectional area. Now, if I assume that all these charges, there are n charges and they all are moving like this, and they all are moving, I neglect thermal agitations here. Okay. Any system will, by virtue of its natural temperature, will have some thermal agitation. So, here I exclude or I neglect those thermal agitations, and what I do, I assume that all the charges are moving with velocity, drift velocity v. So, v is the drift velocity. So, from 603 you must be remembering the drift velocity. We have seen that charge carriers under constant electric field can drift with a constant velocity. So, this is the drift velocity of the electron, of the charge. Okay. So, now I can assume that in time, small time dt, in small time dt, the charge carriers will move a distance v into dt. Okay. So, I write here that in time, in small time dt, charge carriers will move a distance v dt. Is it okay? So, now I assume that the length of this section, this is a small piece out of a long pipe. Okay. So, I assume that this section is v dt long. I assume that this section is v dt long. Okay. So, what will happen, that all the charge carriers that are entering will come out after dt time, there will be nothing inside. Okay. So, all of them will come outside. Now, I can calculate the current that is coming out of this surface. Okay. So, the current coming out in dt time will be equal to total charge that is entering into this volume per unit time. That will be equal to the total charge that is entering into this volume per unit time. And I know that there are no sinks in between, that I have assumed. So, it means all the charge that is going to enter is going to come out, and the direction of the current will be perpendicular to the surface area. The direction of the current will be perpendicular to the surface area. Okay. Current will come out like this. So, if this is my surface, then the current will come out like this. Okay. So, this is perpendicular to the surface. So, in that case, I can say that the total charge will be equal to, what will be total charge? I can write it like this, or I will say total current is dq by dt. Current will be dq by dt, and I can write that this is due to the total charge that are entering into that volume, and I can write that this is equal to q into n, because n is the total number of charge carriers per unit volume and q is the species type of charge. Q into n v dot n, where n is the unit vector perpendicular to the cross sectional area. Okay. Just to ensure that my current is always perpendicular, v dot n dt into dA divided by dt. ठीक है? This is I will write down here. So, I get I is equal to q n v dot n cap into dA. Okay. Now, if you remember your 603 semiconductor device physics, then you would remember that this is the current density and QV is the current density. So, what I get here is that I is actually equal to integral over an open surface is equal to j dot n dA. I get I is equal to integral over an open surface j dot n dA. Okay. Now, I can apply the divergence theorem here, and I can write that this is equal to the current. I am going to rub this off. Okay. So, now by applying the divergence theorem, I can write the right hand side as integral over V del dot J dV, where what is V? V is the volume which is enclosing that surface S. Okay. What is my surface? My surface is this cross sectional area. Now, any volume that is going to enclose this surface is this V. So, I can write that I is equal to del dot J dV. Okay. Now, I will have a negative sign also here. This negative sign is very important. Now, why? See, we considered that I was equal to, that I was resulting from the charge that is entering into this volume. I assume that the current is actually due to all the charge that is entering into this volume. Okay. So, I was actually that I is equal to the current that is entering into this volume. But when I am considering a system, I will be interested in current that is coming out of a particular volume. So, this is the current coming out of this small section. That is why that negative sign. Okay. That is the reason for that negative sign, because I actually, when we initially calculated, it was the current that was entering into this surface. But here we are interested in calculating the current coming out of this surface area S enclosed by volume V. So, that is why it is del dot J dV. Okay. Now, from the definition, I can also say that current is equal to the total rate of change of charge enclosed in a volume. I can say, okay. Current can also be, by definition, electric current is total rate of change, or you can write here time rate of change, that is more precise, time rate of change of charge enclosed in unit volume. Okay. So, I can write, let this be equation A. So, by using this definition, I can also write that I is equal to d by dt integral over V rho dV, right. Rho dV is the total charge enclosed in a volume V, and rate of change of this charge is equal to the current. This is by definition. Okay. So, from, if I subtract, this is B, if I do B minus A, what I will get? If I do B minus A, what would I get? If I do B minus A, what is the result? बताइए. I get integral over V del dot J dV plus d by dt integral over V rho dV is equal to 0. We get this? Okay. Now, this volume V here is arbitrary, you can choose anything. So, I can easily leave this integral sign, and what I get here is del dot J plus d rho by dt is equal to 0. This is your continuity equation. Okay. This is the continuity equation. Now, what does it tell? It tells me, this continuity equation tells me that charge and current continuity equation tells me that charge on a surface and current coming out of a surface are closely related. Okay. They are also closely related. The charge density and current density are closely related, and the differential equation governing this relationship is called the continuity equation. Okay. So, it means if current is coming out of a surface, it means inside that surface the net amount of charge is continuously decreasing. Okay. Because the continuity equation is based on the fact that charge can neither be created nor be destroyed. So, if current is coming out, means charge are being consumed. So, if charges are being consumed, it means net charge which was within this surface, this small section is continuously decreasing. So, this continuity equation gives me a balance between charge and current, that if current is increasing, it means charge is decreasing. If from a surface current per unit volume is decreasing, it means charge is there, it is building up. Okay, slowly it is building up. So, that is this continuity equation and very important equation. So, this is the now I will show you an interesting fact that this continuity equation is embedded into the Gauss law. This continuity equation is embedded, it is inbuilt into the Gauss law. Okay, that we will see now. So, from Gauss law I know that del dot E is equal to, the first Maxwell's equation says del dot E is equal to rho over epsilon naught. Okay. This is the basic equation. Now, if I take the integral, I can write this as integral E dot dA. I apply the divergence theorem. I say E dot dA is equal to, I write the epsilon naught here and I write over S, this is surface charge density, then I have rho S dot dA. Okay. E dot dA is equal to rho S dot dA, right. So, now if I take the derivative, time derivative, if I take the time derivative, I will get here epsilon naught d by dt of E dot dA is equal to integral over S d rho S by dt into dA. What is this? This is Js. This is the surface current density, d rho S by dt is surface current density. So, what I get here is that epsilon naught d by dt, or I take it inside epsilon naught E is equal to integral over S Js dot dA. Here I have dot dA. Okay. Now, this I know this is the integral form of the Gauss law. This is the integral form of the Gauss law. Okay. And I can simply replace the whole stuff by rho. I can simply replace the whole stuff by rho. So, I can write here d by dt integral over V del, I take the epsilon naught outside, del dot E dV is equal to integral over S Js dot dA. So, this del dot E is equal to del dot E into epsilon naught will result in rho. Okay. So, I can write here that d by dt integral over V, d by dt integral over V is equal to rho dV integral over S Js dot dA. Okay. So, if my current is positive, again by the same in logic, if my current is increasing, then rate of change of charge should be negative. Okay. So, I apply a negative sign. So, when I do that, I get an equation which throws more light onto the current and charge relationship. So, I can write here that integral over V d by dt rho dV plus integral over S j dot dA is equal to 0. And it tells me, this equation precisely tells me, the same equation is same, but it is written differently, and you can see that it is entirely derived from Gauss law. We have not used anything else. So, it means this continuity equation is inbuilt in the Gauss law. And what does it say? It says that if the current coming out of a surface, current is not in the volume, current coming out of a surface S, if it is increasing, then the net charge enclosed in volume V is going to decrease. Okay. So, this gives a more clear picture of the relationship between the charge and the current. Okay. This is the continuity equation, and this finishes your unit 1 also. So, if you have any doubt from continuity equation, you can ask me now. And I tell you that precisely this was the reason why Maxwell added the second term, displacement current term, in the fourth Maxwell's equation. It says, the fourth Maxwell equation says that del cross E is equal to mu 0 j plus mu 0 epsilon 0 del E by del T. This is del cross B, right. So, now if I look at this equation, if suppose I have a capacitor, the example that we had taken yesterday, and if this current, this term was not there, if this term was not there, then neither any current would have entered into that capacitor, and there would have not been any current coming out of the capacitor, because this term is 0, and I know that there is an insulation in between. So, current can neither enter nor come out. So, it means although there are charge, I know current is going in, and it means if no current is coming out, it means all the charge is destroyed. So, basic premise of the fact that charge can neither be created nor be destroyed is violated. So, Maxwell was compelled to add another term of displacement current. Okay. This was the reason, one of the reason why Maxwell had to add this displacement current to the fourth Maxwell's equation. Okay. So, that is all for today.